All right, guys, let's talk about waves and light and energy. This is a really interesting topic in chemistry. Before we start, let's just talk about the type of waves that we're discussing here. So we're talking about waves from the electromagnetic spectrum. And all of those waves are transverse waves. They look like this. They're the kind of waves that you think of sort of wave looking. And in the spectrum of waves, in the electromagnetic spectrum, we have waves that are very, very tightly packed like this. We would say that these have a very high frequency and a very low wavelength. So low wavelength and high frequency. That's the variable that we use for frequency. It's like, kind of looks like a V. It's not really a V, but if you're comfortable with it as a V, that's great. And then we've got, on the other side of the spectrum, we've got really, really big waves like this. And here we have a very high wavelength. This is the symbol for wavelength. It's a Greek letter, lambda. And we have a very low frequency. Okay? And the difference between the types of waves from very, very short wavelength to very high wavelength is the amount of energy that's in those waves. So these low wavelength, high frequency waves, these are high in energy. And these guys here, the low wavelength, the low frequency and high wavelength, these are very low energy waves. But the thing that's the same about them is that all waves from the electromagnetic spectrum move at the speed of light, okay? And that speed of light is 2.99 times 10 to the 8th meters per second. And that is really, really cooking. That's a very, very fast speed. Okay, so whether the wave is a high wavelength or low wavelength wave, they all move at the same speed. And that kind of explains the energy. So we know that the energy is basically, it looks at the amount of waves that would pass a point during a given time period. And so here with this low wavelength, we see many, many wave crests that would pass by a point during a given time compared to these low energy waves here, okay? So there's some easy calculations that you can make here. And so take this down. We're gonna do a little graphic here, 2.99 times 10 to the 8th power meters per second. This is the wave speed. And we can use this wave speed to calculate either the frequency or the wavelength of an electromagnetic wave. So over here we can, let's put our frequency. And this is usually measured in hertz. And again, with its little symbol, sort of looks like a V. And then over here we're gonna put wavelength, which is Greek letter L. Now, it's very important, wavelengths can be given to you in different distance units, but you've got to make sure that you're working in meters. And so sometimes if you're given a nanometer measurement for a wavelength, you've got to get this to meters so it matches your wave speed meters per second. You can't divide to unlike distance terms, okay? So anyway, make sure that you do that. And now if you were going to calculate, like if a question said, we've got a wavelength of 1.04 times 10 to the 8th wavelength, and we want to know what the frequency of that wave is. So what is the frequency? You would just cover up the term that you're trying to solve for, and then it's basically just the speed of light divided by the wavelength. And so you would just, on your calculator, make sure your terms are in parentheses and divide that by the wavelength that you've been given. That's probably a -8, by the way. And make sure both of those terms are in parentheses. And you just pump it through your calculator, and that's that. Another bit of math that you're going to be responsible for is calculating energy. And that's measured in joules, if you remember. And so to do that, it's the same sort of little math graphic here. We're going to take our, we're going to have different things down here. This is going to be something called Planck's constant. And I don't have time to get into what this number really stands for. For our purposes, we're just going to use it as a constant value, and it's a pretty funny number. It's 6.626 times 10 to the negative 34th power. Okay, so that's just a constant value that you're going to use in any calculation to find your energy. And then over here, you're going to use your frequency value. And so if you've been given a frequency for a wave, you can just divide your energy value by Planck's, you can multiply, your frequency by Planck's constant to get energy, okay? Or if you've been given the wavelength and you want to know the energy behind that wavelength, you would first have to use this to solve for frequency, and then substitute that frequency in here, multiplied by Planck's constant to get your energy value. So hope that helps.